Hello. We are doing another Discrete Mathematics and its applications problem. I am using the 7th edition. So for me, this is chapter 5.1, question 23. If you're using a different version, the chapters and questions might not align, but the problem should be in any edition of this book or different books. Hopefully, if you are searching for the problem itself, the Rosen discrete math part won't matter. So what we are doing today is we're looking for which negative integers n is 2n plus 3 less than or equal to 2 raised to n, or 2 to the nth power. Now, non-negative integers, n is an integer, so that means that n is greater than or equal to 0. So the first thing we'll do is run through some integers starting at 0 to see if this holds, and then we'll conjecture based upon what we find, and then prove by induction that our conjecture is correct. All right, so the first thing we're going to do is run through some of these integers. So first thing we're going to do is try 0, obvious place to start. If you have a little more intuition of where to start, you don't have to start at 0, but just as for an illustration effect here, I'm going to start at 0. But it should be obvious that this is not going to be true. 2 times 0 is 0. 0 plus 3 is 3. Anything raised to the power of 0 is 1. So this is a little fact in case you forgot. So that does not hold. N equals 1. Does that change anything? Not really, right? Because 2 times 1 plus 3 is 5. And 2 raised to 1 is just 2. So what we're saying here is 5 is less than or equal to 2, and that's not true. How about 2? Does 2 get us closer? So 2 times 2 is 4, plus 3 is 7. 2 squared is 4. And 7 is not indeed less than or equal to 4. So let's continue. Let's try n equals 3. So 2 times 3 plus 3 is less than or equal to 2 to the third. So we're saying here 6 plus 3, 9. Is that less than 8? Of course not. So that doesn't hold. Maybe you're thinking we're going to be here all day. Well, bear with me. 2 times 4 is 8, plus 2 or 3 is 11, is less than or equal to 2 to the fourth is 16. All right. So we found the first one that's true, just to convince ourselves and that we haven't been fooled or did the math wrong in some sense. Let's look at the next case, and it's 5. So 2 times 5 is 10, plus 3 is 13. And that's less than or equal to 2 to the fifth is 16 times 2, which is 32. So yes, that holds. We can see that the pattern here on the left side of the inequality growing up by 2. And then on the right, we're obviously going up by a factor of 2 to some n. So you, like I said earlier, if you have a better guess, you could have probably started with 3 or 4. But just so to be thorough, this is what we get. So based upon this, let's conjecture that 2n plus 3 is less than or equal to 2 to the n for integers n, and let's say greater than or equal to 4 instead of greater than 3. Just, you could have done either. Let me write that. I'm going to use greater than or equal to 4, but you could have done integers greater than 3. Same thing. All right, so this is our conjecture. Conjecture means that we're not entirely certain it's true, so let's prove it. Our proof is by induction. This is not necessarily by choice. I'm not choosing to do induction. I'm just following the question that was posed in the book. You could maybe do a different method to prove this, but it asks you to show this by induction. So That's what we're going to do. So induction proofs, we always start with a base case. And the base case here is P of 4. In other words, that's our first term, is where n is 4. Now, we did that above here. We don't necessarily have to repeat it. So we showed above that 11 was less than 16. So the base case holds. Ruby's upset if you hear her barking. Somebody has asked why Ruby isn't in these videos. Cheekily answered that because she's not very good at proofs. She's much, much better at calculations, and she loves calculus. So maybe in the future, we'll get Ruby up here to do some math. But for now, she does not like induction proofs. So the base case holds. Let's look at the inductive the inductive step. The inductive step, we're going to first state the induction hypothesis, then we're going to show what we want to prove, and then we're going to prove it using usually algebra. With inequalities, we're going to build inequalities, and put them together at the end, and then by transitivity, we'll show that what we need to do is in fact true. So the induction hypothesis is that we're going to assume true that for some value k less greater than or equal to 4, that 2k plus 3 is greater than or equal to 2 raised to k. Again, this is for integers greater than or equal to 4. This is the induction hypothesis. I like to write IH. I like to put that in my proof so that when I go back and look at it, this is a habit I picked up as an undergrad math major. When I'm done, I can read back and say, here's where I use my induction hypothesis. I've stated in other videos that this is a habit that I picked up because a professor had once mentioned that when I was an undergrad, that if we are proving by induction and don't use the induction hypothesis, that something most likely went wrong or we made some assumptions we shouldn't have. So this was always a habit I had. And again, I'm writing a lot as an illustration. You don't necessarily have to write this if you're proving this for a class. This is really just an explanation, not a complete, rigorous, and copy and paste proof. So you should always write proofs in your own words, in your own style. Professors always have preferences of how proofs should be written. I'm using a very specific method that I learned. So just take that as you need. So this is the induction hypothesis. Here's what we want to show. Again, another habit. I like to write down what we need to show. This is the p, k plus 1 k, so it's the next term after k. Or it's literally, I'm going to replace in the induction hypothesis k with k plus 1. So this becomes 2 times k plus 1 plus 3 is less than or equal to 2 raised to k plus 1. Put a question mark because that's not necessarily true. That's what we want to show. This is our task here. As required by induction, we show up to k, we assume that's true, and then we show the next case, k plus 1 is true. Like any induction proof as well, we're going to start on one side of this inequality. I'm going to start on the left-hand side, and we're going to start to build inequalities so that we can indeed show that the left-hand side is less than or equal to the right-hand side. So let's look at 2 times k plus 1 plus 3. Now, I can distribute the 2, so I get 2k plus 2 plus 3. And I'm going to do, maybe let's call it a trick, but it's not so much a trick as I'm trying to use the induction hypothesis. And so I'm going to write this just by grouping what we have this way. Integer addition is commutative, so I can add in any way I want. And then I'm going to group this, so I have 2k plus 3 plus 2. So why do that? Well, because by the induction hypothesis, we stated that 2k plus 3 is less than or equal to 2 raised to k. So 2 is greater than 0. It's positive. It's not going to affect it if it weren't, but just as a good habit, check to see that if you're going to add, subtract, multiply, or multiply by a fraction, that your integers are positive and it doesn't affect the inequality itself. Now, addition by a positive or negative number will never affect the inequality, but multiplication obviously would. So we're going to add 2 to both sides. And both sides, I mean both sides of this. So that becomes, let me write out the complete left-hand side. That is equal to 2k plus 3. Now I'm adding the 2 to both sides of this guy. So that's plus 2 is less than or equal to 2k plus 2. And 2k plus 2 is the same as saying 2k plus 2 to the 1. Mostly because I want to be able to write this a certain way. All right. Now, let's look at this. 2 raised to k plus 2 raised to k. If I want to think of this particularly as a single base raised to some power, we can think of this as being a factored out 2k, then I get 1 plus 1, which is the same as 2 to the k times 2, which is 2 to the 1, which is 2k plus 1. So as an aside, this is where we're heading. Now let's look at our inequality here, that 2k plus 2 to the 1. Now, 2 is certainly less than 2 raised to k, because k, we said, was greater than or equal to 4. So the only way that this is true is when k is 0, 1. So this is true. And we're going to add 2 to the k to both sides. This, again, will not affect this inequality. But just to be sure, what we're saying is that 2k essentially is positive. So we are in no danger. So I'm going to add that. And we showed above in our little aside here that 2k plus 2k is the same as saying 2 to the k plus 1. So if we put these inequalities all together, then we get this. So this is how I like to show it. I like to build the inequalities, then put them together so that we can see. And again, if you write up a proof, you don't necessarily need to do all of this. Just I'm trying to illustrate this as clearly as I can. So we are at the point here where we started with 2k plus 1 plus 3. We said that was equal to 2k plus 3 plus 2, which we showed that is less than or equal to 2k plus 2 to the 1, which we again showed that is strictly less than. Now this doesn't really matter, but we can write less than or equal to. But we know for our values that that's true, and this is 2k plus 1. So therefore, we have shown that 2k plus 1 plus 3 is less than or equal to 2k plus 1. And that's it. That's the k plus 1 case. My writing here is not the best, so let me just write this better. So this is what we wanted to prove. So therefore, our 2n plus 3 is indeed less than or equal to 2 raised to n for values of n greater than or equal to 4. That's it. QED. I like the box. And that's it. We are done. So hopefully this was helpful and the steps were clear. Let me know if you would need anything additional, if there's any other problems from this text or from math, the world generally that you want to see, and we'd be happy to try to produce a video for this. And thanks for watching. Like and subscribe, and we'll see you next time. Thank you.